Hello, this is Further Maths Statistics, exercise 9b. It's actually the very last exercise that we need to do for Further Maths Stats, so let's go on and do it. First of all, look, what we are trying to do is very often we are asked to find confidence intervals and for the mean mu. So in other words, if I thought, if I was trying to find what the actual mean was for some data, it might be, or a distribution, it might be that I do a sample to see what that mean value is. And of course, all you ever get is X bar. It's the sample that you took, the mean for the sample. And you kind of hope one's close to the other, but it obviously isn't exact. And so the question is, how far left or right of that value would we be happy to accept? You know, that it might have been really, we might get this to be 27. We might have thought the mean was 30. Is this close enough? That's really what we're doing here. And what we do is we kind of end up, we draw ourselves a normal distribution curve. Down the middle is what we actually get from our sample. And we try to find what are called confidence interval values, like limits of the interval at which we begin to doubt whether or not the X bar is accurate to the mean, the mu value. So the old system for doing it was to use it was this Z value. It was called standardized variable. We're not going to do that. We're going to use a different method. But we're still trying to do the same thing. We're trying to get a value here. There's one value. We're trying to get a value over here. And between these two values, we would be happy to accept H0. Beyond them, we'd say H0 is not true. And we reject it. This distance all the way across is often called a width. And again, this was the posh way of finding the width, but we're going to try and do it via new means rather than using these outdated symbols now. So on the class widths, what are we doing? So I'm going to draw it down here. So on the class widths, we are going to try to draw a normal distribution curve. It says assuming you do a sample and you get 350 as your mean. So imagine I do a sample and I get 350. There it is. And it says what sigma is. We've got a square root 105. A sigma equals 105. Be aware that sigma squared then is 105 squared. And my sample becomes sigma squared over n, doesn't it? You know this is the sample variance, or the unbiased estimate of it, perhaps our best version of it. Our sample variance in this case then would be 105 squared divided by 15, and I suppose my standard deviation then is the square root of 105 over 15. So bear that in mind. What we're going to try to do is start off by finding this value here. This x value here, which I'm going to call x. You'll notice I want a 90% confidence interval. Now it's symmetrical, this thing, so 90% represents the middle bit, and as you can imagine therefore, this bit here is 5%. And this bit here is 5% as well. So for that reason, we can say the area on the left-hand one that I'm trying to find, this x, is 5%. So this is what I type in. I press menu. So everyone press menu, 7 and 3. We're doing an inverse normal. It's an inverse normal because I know the area already. It's 0.05. I have to type in this standard deviation. Now you can type it in like that. I actually simplified it. I typed in 105 divided by root 15. The mu is 350. Well, technically it's actually the X bar, but we're using this button to do what we want it to do. And you just press equals, and it comes up my calculator 305.406 and a bit, but I've rounded it. And we can do the same thing for the other side, and you can imagine if that's 5%, 5% at the other end, up to this point here, if I want to find this point here, another X value, I've got 95% to the left of it, because I go all the way back here as well. So for the right hand one, I do 0.95. Same square, sigma, same mu, but I get a different value here. Type that in, see if you agree. And this gives me my confidence interval. It is that easy. That is the confidence interval that I want to use. Now, can I use it? Well, we'll see that in a bit. But that is how I find the confidence interval, using this menu 7 inverse normal. I've already got the answer here, but I'll do it anyway. Assuming that this is a normal distribution, find the confidence interval for a 99% confidence interval. So again, we'll do the same thing. My sample, I got minus 1.8. What a ridiculous number! But there you go. It's a negative number to start with. So my real sigma squared over n is going to be 14 squared over 6. So you can imagine if when I type this in, I don't type in 14, I'm going to type in something based on this. So on 99% again, so my middle numbers are now 99%. That only leaves 1% for each end. It actually leaves 0.5% for each end, 1% between them. So that's 0.5%. You can imagine my area has got to equal 0.5%. So I'm going to say, I'm not sure if I've got the answer, that I haven't. My area at this end then is going to be 0.005. Let's do it now, menu 7.3. Area is 0.005. My sigma is going to be the square root of 14 squared divided by 6, close bracket. My mean was minus 1.8, don't like that at all, but there you go. And my left one, when I've typed all that in, it says minus 16.52. My area for the right hand side is exactly the same as everything else. It's 0.995, 99.5%, because I've got 0.5% left over on this side. So again, just change that 0.995. Everything else stays the same, and I get 12.92. 12.92. And you can see why then I've rounded those numbers to 3 significant figures, and that's my confidence interval. Again, the calculator does all the work for me. Let's use the calculator. It is known that the mean length of a rare type of frog is normal with variance 14. Alright, now this tells me something about the variance. They tell me the variance is 14. I think the others have done the same. They've given me a lot of this information. A sample of 8 frogs are measured. So again, I can type this in. 95% confidence interval. So something like this is going on. I have got the mean was 20, and I want the confidence interval for it. So 95% is the middle part, and you can imagine it's 5% left over, and each end therefore is 2.5%. 2.5%. And so for the left hand side, I'm going to type in area equals 0.025, 2.5%. Yes, that's right. So 0.025 is the area. The sigma, what was the sigma? It was 14 for the variance. So I'm going to type in the square root of 14 divided by, the variance was 14, not the standard deviation, divided by 8. And the mu, what was it? Mu was 20. Really, it's the x bar, but should be getting used to. So I get 17 and a bit, 17.41. On the right hand side, I type in the area to be 0.975, 2.5% left over. So let's do that again. 0.975. Leave everything else the same. I get 22.59. So you can see, rounding those, hopefully I got the right answer, 17.4 and 22.6. This is not hard once you get used to using the calculator to do the work for you. Okay, notice the way it's written. The time taken to complete a test is known to be normal with variance 18.4. It is very similar now, isn't it? So I'm going to draw a normal distribution curve. I'm a sample of 20 students, and the mean time is 42.1. So 42.1. The variance is 18.4. So again, what we're really saying is that x bar is normal. 42.1 was the mean, comma, and it's 18.4 divided by 20. And of course, I've got to square root that to get my... Now, it wants an 80% confidence interval. So you can imagine that's 20% left over, 10% each end. This is 10%. And this is 10%. So we just got to get good at knowing what areas to type into our calculator. For the left hand side, I'm going to type in 0.1. So let's do that. 0.1 for the left. Sigma is the square root of 18.4 divided by 20. close bracket. The mean was 42.1, and that gives me a left-hand value of 40.87. The right-hand side, obviously, if you've got 10% left over on the right, you've got 90% left to the other side. And if I just change that to 0.9, I get a value of 43.33. So rounding, hopefully I've rounded 40.9 and 43.3. Perfect. I'm tempted to leave this one out. I might come back to this and save this for the lesson itself. But one thing I want to show you is what happens if it is not normal to start with. We've already seen that normal distributions, this works for fine. But what happens if it's not normal? And the answer is we can use the central limit theorem. And the central limit theorem says, well, as long as you use the unbiased estimate, that's fine. Just use the unbiased estimate and everything else stays the same. So if everything else stays the same, let's have a look at this. We've got 100 new light bulbs were installed, and 3 months later they had all failed. The data for the times that they had lasted were these. Okay, so we had 100 light bulbs, and 3 months later they've all failed. So the time for each bulb is added up, and we've got this. So presumably we can do T bar equals that sigma T over N, which is 10500, and we divide them by 100. So no one's going to be surprised to learn on average they last for 105 minutes. The standard deviation, well, I could work out that. Why don't we just go straight to the unbiased version? The unbiased version says ST squared equals, and I won't have to square root it then, it's N 100 over 99 times by, and it's 1712500 over 100 minus 105 squared. And that, presumably, is something I can type into my calculator. Let's do it now. Menu 1. 100 divided by 99 times by bracket. So I've typed it all in, and I've got an answer of 6161. 0.6161. It obviously goes on forever, one of those. 6.2 them. So on that basis, we now know that our T, the time bar, normally x bar, but I've written T bar, is normally distributed, mean of 105, and variance 6161.62, rounding. We would therefore expect it to be a close approximation to the value I would have expected to get, not necessarily the perfect one. So I've got 105. What is the confidence interval? Now they've said a 99%. So you can imagine it's 1% between the two, it's 0.5% each end. We've done one of these before. The left hand end will have an area of 0.005. So I'm going to do that now. So menu 7.3, 0.005 area. What's my sigma? Well, the sigma was, I've got to type in the square root of 6161.62, still divided by 100. Got to divide by 100. And I get 7.8ish. And my mu I got was 105. What am I? So I get, on the left hand side, 84.78. And the right hand side of that, so if you like, I'm trying to find this value now, I shall use 0.995. 0.995. And I get 125.22. So my confidence interval is those rounded 85 to 125. Okay, I did it to the nearest hour. That's what they wanted as well. Now look, notice then that it was almost identical. Doing this was identical for the ones which I needed to use the central limit theorem for as it was for the other ones. It was the same process. The only difference was I had to calculate the mean and the variance first on this example. Now I've got one more example of this to do with you, and then we'll do exercise 9b. So in total there's 2 questions I still need to do in class. But that feels as if that's doable. The calculator does so much of the work for us. The old method was quite painful, whereas this method's quite nice. So fingers crossed, that should be it for further maths statistics.